Hi, I'm Devin Boyles, and this is Spin in the Rain / Hat in the Intro.
And now for something completely different.
Face it, you're either on one end of a Nerf weapon or the other. Time to choose. So, you better think about getting yourself a bow and arrow or a Nerf missile storm. Excuse me, don't you just love this? Or an arrow storm. Or a very good hiding place. Don't you get it? It's Nerf or nothing.
Nerf guns. Are they really as innocent as their advertising makes them appear to be? Maybe. Or maybe they're breeding a new generation of disgruntled killers in our own backyard. Who knows? Can't really be sure. One thing we can't be sure of, with the evolution of more realistic and sophisticated weapons, we'll be sure to see stranger and stranger creations from the underground Nerf community. Take this one myth, for example. So, like all good things, this myth came from the internet. According to the myth, there's this guy. We'll call him Dax Scoot. So Dax's outside playing with his Nerf gun when he realizes that it kind of sucks. So what does he do? He throws it on the ground and gets to work. Starts ripping it apart, throwing pieces away, putting pieces in. He gets a hot glue gun from somewhere. He does some alchemy. He's pretty much Dr. Frankenstein all over this gun. This goes on for a while, but when he gets up, what does he have but the bossest, most epic modded Nerf gun ever? And what does he do with his newly forged monstrosity? Shoots it across a football field. Yep, all 300 feet, 100 yards, or if you're feeling real technical, 91.44 meters. So is it true? Did Dax Scoot really make a Nerf gun that shot all the way across the football field? Probably not. But in the spirit of science, we're going to try and replicate his results anyway.
For the first test, we got our lovely assistant Zach here. Zach, wave hi to the camera. Alright, so we got Zach is going to shoot 5 rounds from each of the guns, holding the gun at level, and we're going to see the average distance each one shoots. And go ahead, Zach. So Zach's shooting the Maverick. Alright, go ahead, Zach.
Alright, kill shot. Nah, I'm just kidding.
You ready?
Oh, wow.
Try and hold it level.
Hit it. Boom. Good measure. It has 6.
Yeah, but we only have 5 spots in the data table.
Well, I know where it landed.
Alright, so this time Zach's gonna try it and see if it can't work this time. Recon, 5 shots, average distance, go ahead. Alright, so Zach is recording the data from each bullet.
Exhilarating.
While Zach's over there guns. Since we only have one weekend to do this entire project, I'm going to save some time and start working on this one.
Say that, Mr. Pat's gonna get pissed. He's gonna get mad at you, Devin. Oh, real.
Alright, so we have our crack scientist Zach going to work on the averages on these guns. So this is basically our control setup, and thus far our findings are that now they really aren't shooting a whole football field.
So after recording all the data and averaging all the trials, we found that by far our best gun was the Maverick, with an average distance of 36.764 feet. And even so, that's only 12% of our target range, so we know that we're definitely going to have to do some modification or scratch build a Nerf gun. And what we're going to try first is using a Nerf gun that we could not test because it didn't fire the same ammunition. So hopefully we'll be able to mod that and see what happens. And then if that doesn't work, we're going to try building our own from scratch. Theoretically, the muzzle velocity of the dart should be equal to the following formula. V equals square root of 2 kd over m times delta x, where k is the spring constant, d is the distance the spring is compressed, m is the mass of the dart, and delta x is the length of the barrel. The equation is found using the following method. By Hooke's law, the restoring force of a spring equals the spring constant multiplied by the distance it is compressed. By Newton's second law of motion, the net force of an object is equal to its mass times its acceleration. This can be rearranged to indicate that an object's acceleration is equal to its net force divided by its mass. Because the force is generated by a spring, we can make the substitution specified earlier, making the object's acceleration equal to the spring constant multiplied by the distance it is compressed divided by the object's mass. This value can be substituted into the following equation. V final squared equals V0 squared plus 2a delta x. Because the item starts at rest, the initial velocity is 0. Therefore, its final velocity squared equals double the acceleration multiplied by the distance it travels. By taking the square root of this, we arrive at the equation V equals square root of 2 kdm delta x. Unfortunately, this equation fails to take into account several factors. First, the force of the spring is not perfectly transferred to the dart. Rather, the spring forces a plunger to accelerate, which generates air pressure. That brings fluid dynamics into play, and I'm pretty sure no one understands that. Additionally, the friction between the dart and the barrel is not accounted for, which would further decrease the muzzle velocity of the dart. To optimize the distance of the dart, we have to set up the function d theta equals vxt. Because Vx equals V cosine theta, the equation can be rearranged into cosine theta times t. Because the basic principles of projectile motion, we know that delta y is equal to Vyt plus 1/2 gt squared. Because of the parabolic nature of projectile motion, and since symmetry is our friend, we know that on level ground, the change in y for the entire flight is 0. Substituting negative 10 meters per second squared for g, we can now do some algebra and rearrange the equation to read as t equals Vy over 5. We know that Vy equals V sine theta, so we set t equal to V sine theta over 5. Using all the above information, we arrive at the conclusion that V cosine theta times V sine theta over 5 is equal to d theta. Warning: calculus content inbound. If you have no experience in calculus, please exit the room or cover your ears. To optimize the function of d of theta, we first need to find the derivative of d of theta. Because v and 5 are both constants, they are removed in taking the derivative of d of theta. By the product rule, we find that d prime theta equals sine theta times negative sine theta plus cosine theta times cosine theta, or negative sine squared theta plus cosine squared theta. Because we are maximizing the equation, d prime theta is set equal to 0. Therefore, we find that sine squared theta is equal to cosine squared theta, meaning that sine theta equals cosine theta, which occurs exclusively at 45 degrees, making that the optimal angle for distance.